created by Mindsticks Foundation Trust.
Namaste and a very warm welcome, learners. Today we are diving into the fascinating world of arithmetic progressions in this explainer. Here is our agenda for today. First, we will look at patterns and number sequences. Second, terms in a sequence. Third, defining arithmetic progression. Fourth, finding the common difference. And finally, we will be solving practice examples together. Let's get started.
Section 1. Patterns and number sequences. It's all about finding the order in numbers. Let's look closely at this first visual pattern. I want you to observe these groups of circles. In the very first column, we have just one single circle, right? Move to the next, and we have 3. Then we see 5, and then 7. Do you see what's actually happening here? It's not random at all. The count of circles is predictably increasing. We are adding exactly 2 circles every single time to get the next arrangement. It is highly structured, almost like a mathematical staircase. Now, please study this next pattern. Here we have arrangements of triangles. We start off with 5 triangles. Then the next figure jumps to 8 triangles, and the third one has 11. Just look at the numbers: 5, 8, 11. I really encourage you to think about the underlying rule here. How do we obtain the next number from the one right before it? Yes, exactly. We are simply adding 3 each time. This simple rule allows us to confidently predict what the next, or even the 100th arrangement will look like. Because of rules like the ones we just saw, we can formally define what we are looking at. It's called a sequence. So a sequence is simply a set of numbers where the numbers are arranged in a definite, predictable order. Think about when students stand in a neat row for a drill on the school playground. There's a first student, a second student, a third, and so on. There's a definite, undeniable order. Well, numbers in a sequence behave in exactly the same disciplined way. Moving on to Section 2, terms in a sequence, let's learn how we go about naming these numbers.
So, you might be wondering, how do we name these numbers so we don't get confused? We use ordered terms. The first term is denoted as T subscript 1, or simply T1. Sometimes we also just call this very first term A. The second term is T2. The third term is T3. That small subscript number simply tells us the exact location of that term in the line. So if we are talking about a term somewhere way down the line, say the general nth term, we elegantly write it as T subscript n, or Tn. It's a very neat, very logical system, isn't it?
Let's jump into Section 3, defining arithmetic progression. This is the core mathematical rule of our explainer today. I want you to direct your attention to the pink arrows you see here. Look at the first sequence, 100, 70, 40, 10. The arrows show us exactly how the next term is obtained. We are taking 100 and adding a negative 30 to get 70. Then we add negative 30 again to get 40. In the second example below it, we start at negative 7, add positive 3 to get negative 4, add positive 3 again to get negative 1. By adding a very specific, constant number, step by step, we generate the entire progression. So the crucial point to take away is this formal definition right here. An arithmetic progression, which we commonly call an AP, is a sequence where the difference between any 2 consecutive terms is always constant. What does that mean? It means if you take any term, let's call it Tn plus 1, and subtract the term exactly before it, Tn, that resulting difference must not change anywhere in the sequence. It remains absolutely rock steady. Section 4, finding the common difference. This is where we truly understand the secret key, D. Here are the essential facts you must absolutely remember. This constant difference we just talked about is denoted by the lowercase letter d. The formula to find it is actually quite simple. D equals the next term minus the current term, or Tn plus 1 minus Tn. Now please pay special attention to this third point, because this is a common trap. The value of D doesn't just have to be a positive number. It can be positive, it can be negative, or it can even be precisely 0. Because of this constant adding of D, the terms of an AP generally look like this. The first term is A, the next is A plus D, the next is A plus 2D, and the pattern beautifully continues. Let's anchor this math in a real-world scenario so we can really grasp it. Look at Arifa's savings table. Arifa has a wonderful habit. She saves exactly 100 rupees every single month. In month 1, she has 100 rupees. In month 2, 200. In month 3, 300. This real-life habit literally creates an arithmetic progression. Here, our first term, A, is 100, and our common difference, D, is clearly a positive 100. And this next example brilliantly illustrates the other side of the coin. Consider Pranav. He borrowed 10,000 rupees from a friend and is repaying it by 1,000 rupees every single month. Let's look at his remaining balance: 10,000, then 9,000, then 8,000. Here, the first term is 10,000. But to get to the next term, we are essentially adding a negative 1,000. This perfectly shows an AP, where the common difference D is negative. Now, there's one more important distinction we must make clear. An AP can be either finite or infinite. A finite AP eventually stops. It has a final term. For instance, Arifa's savings over exactly 12 months is finite. Pranav paying off his loan completely is finite. It will reach 0 and stop. An infinite AP, on the other hand, goes on forever without an end. Think of the multiples of 5, 10, 15, 20. There is absolutely no final term there. It just keeps going. Which brings us to our final section, Section 5, Solving Practice Examples. Let's study these together. I want you to grab a mental pencil, sit up straight, and let's apply the rules we've learned. What's really interesting about what we're looking at now is how we systematically prove if a given sequence is an AP. Look at example number 2. The sequence is 2, -2, -6, -10. Now, is this an AP? Well, we must patiently walk through the subtraction. Let's find T2 minus T1. -2 minus 2 gives us -4. Okay, let's check T3 minus T2. -6 minus a -2, which becomes -6 plus 2. And that is also -4. Because the difference is constantly -4 across the board, we have mathematically proven it is for sure an arithmetic progression. Let's do the reverse now. Let's logically build an AP sequence completely from scratch. What if I tell you the first term, A, is 5, and the common difference, D, is 7? Step 1, write down the first term. T1 is 5. Step 2, add D to find the second term. 5 plus 7 is 12, so T2 is 12. Step 3, add D again. 12 plus 7 is 19. If we just keep going, the next terms are effortlessly 26, 33, and 40. You see how wonderfully easy it is once we know our A and our D? Let's try one that looks just a little trickier but follows the exact same logic. Point your eyes to the first solution here, marked Roman numeral 1. We are building an AP starting with A equal to -3 and a common difference D of +4. Okay, first term, T1 is -3. Next term, T2 is -3 plus 4, which gives us +1. Next, 1 plus 4 is 5. Then 5 plus 4 is 9. Do you see? Even starting below 0, the constant addition smoothly guides us along the number line to create the sequence -3, 1, 5, 9. We have done absolutely excellent work today. But before we finish our explainer, I want to leave you with a small challenge to test your newly acquired intuition. What if an arithmetic progression has a first term A of exactly 10 and a common difference D of exactly 0? Think carefully about what it actually means to add 0 every time. Based on that, what do you think the 100th term of that sequence will be? I will let you ponder that powerful little concept on your own. Keep practicing and keep finding the beautiful order in the numbers around you. Namaste.